So let's begin again. There was a question in the break about there were several questions in the break about the trick in the calculation. Let's see. I wrote this integral. In the following way. So I essentially just swapped where the nabla is working. So it looks like this. Minus sign. Like this. And now why can you swap this? Well, the idea is to start out with a product rule for differentiation in 3 dimensions. So we have quiet. Okay, so f is some arbitrary function, scalar, and a is a vector. And now this is the product rule for this differentiation. Now, what we have here is, of course, a term on this form, right? And I transformed it into an integral on the other form, this term. But what happened to this term? Well, the answer is simple enough. As I move this, let's see, first I move this on this side to get this integral. It's equal to this one with a minus sign, and then this term. And the integral over, let's see, now this is the divergence of a vector. And the divergence of a vector, well, we can use the divergence theorem to change this into a surface integral. And as I'm integrating over all of space, the surface is going to be infinitely far away. And there's not going to be much material somewhere between here and Betelgeuse. So the polarization is 0. And then I can just say that this term is equal to 0. Because this is, of course, equal to the integral. Loosely speaking, 1 over r times the vector times the ds. And I'm integrating over all of space. So this surface is sort of enclosing my whole lab or whatever. And there's no material. Let's say if I make the integral bigger than the planet, there's no polarization. This term just vanishes. That's the idea. So this is, of course, not a rigorous proof, but that's why I call it the motivation. So if you look at a particular system, you usually look at some, let's say, charge distribution in a vacuum where you shine light or at least air, which has very small polarization, and then this is fine. But in principle, something could go wrong with this proof, so don't bet your life on this, setting this to 0. But I hope you won't have to do that. So did that answer all the different variants of that question? Or does someone still have a question about that trick? Okay. Now, a brief summary. So in a vacuum, I can do it here. We have the following 2 laws. the Gauss law and the Faraday law. Like this. Now if I'm inside some dielectric medium, it's going to be in terms of, the Gauss law is going to be rewritten in terms of the D field. And the idea of the D field was to incorporate the polarization effect so that we didn't have to figure out this complicated fashion, how does the E field make a polarization, how does the polarization make an E field, and so on. So the gradient of the D field is equal to the free charge. And those are the charges that are not bound to a molecule from the beginning. And the Faraday law looks the same. And now I'm going to show you why D is not E. There are some important, because you might think that, well, why don't I just figure out equations for D in this one as well, and just use the D field all the time? Why bother with this E field, which doesn't somehow manage to take into account the polarization? It looks just inferior, but it's not so easy. And I'm going to quote some of the differences. For example, in vacuum, the polarization is 0. And then the D field is just proportional to the E field. So in the vacuum, there's no, that's why you might think that it's a good reason to just use the D field. In the vacuum, there's no difference, so to speak. A constant here doesn't change much. But in general, the curl of the D field is not equal to 0. The reason why is, of course, that the polarization does not necessarily have a curl equal to 0. The easiest way to look at this to see why this is so is to look at some interface. So if you have some interface, medium 1 and 2, and then we did a small loop integral over the E field to get the boundary conditions at the surface. Now if you do the same with the P field, you'll see that it's going to be different because the P field is not directly proportional to the E field. I mean, the dielectric constant, it's different in medium 1 and medium 2, and then they're not going to cancel out. So the curl is not always 0, especially at interfaces. So that's a trap. And in general, there's no Coulomb law. I didn't spell that right. Yeah, I did. This, of course, is partially because you have anisotropic media, which might change the D field. We'll look at that. And, well, you just can't construct a Coulomb's law for the D field, except if you're in a vacuum or in a very simple dielectric. That's not always the case. Yeah, and the D field does not have to be parallel to the E field. At least in general. And this is, has to do with what I showed you for the CO2 molecule, that if you apply an external electric field, the material might polarize more easily in some directions, and thus the D field doesn't have to be parallel to the E field. And this, of course, breaks a lot of things. Finally, what we need to solve a real problem with the electrostatic problem with dielectrics is, first of all, these laws, but also you need some sort of connection between D and E field. And these are called constitutive relations. And because in general these connections are very complicated, they might be anisotropic, they might be nonlinear. There's a ton of interesting phenomena, and this is subject for ongoing research, and it will be for decades or centuries, because there's so many things you can do with materials and metamaterials, which you might have heard of, which is essentially if you structure a material in a funny way, you might create something that looks like a material but has very strange, let's say, dielectric functions. For example, you could have a negative index of refraction, you know Snell's law? So, in optics, if this is air and this is, let's say, glass, what normally happens is that a light ray comes in and it's bent towards the surface normal. But if you have a negative index of refraction, it comes out here. Now that's not something you ordinarily see, but this is what you can do. And, well, you need electromagnetism to figure out this stuff. So, the constitutive relation, that's the relation between the D field and the E field. And I'm not going to write it in a specific way, because in general there is none. I am, however, going to show you some special cases, and the most important one is for a linear, homogeneous, isotropic material. It's a nice example because it's so easy, you can easily do calculations with it, and it also happens in a lot of places like windows, your binoculars, your glasses, plastic. And in this case, the connection is really simple, because the polarization is now just proportional to the E field. I factor out a factor of epsilon 0, because it makes this quantity dimensionless. But in the end, the polarization is just a constant times the electric field. This means that these vectors are parallel. And then if you look at the definition of D, which is not here at the moment, but it's just E plus P, right? So it means that the D field is parallel to the E field. So it's a very simple case. Yeah. So the chi here has no units. That's why I took out the epsilon, just to make it easier on the chi. And yeah, E is parallel to E. And now, if I plot this, wow. It's just a straight line because they're proportional. But now let's say if I have some sort of crystal that looks like my hydrogen chloride molecule. Oops. As you remember, the main effect to polarization was that we oriented the dipoles, right? So at some point we're going to orient, I mean, if I just keep increasing the electric field strength, we're just going to orient all the dipoles so we get some sort of saturation effect. And then after that, it's only the induced dipole moments which contribute to the polarization. And this means that we get, in the beginning we get a linear graph when there's still some dipoles to align left. But then as the field strength increases, we run out of dipoles to align. and it falls off like this in some fashion. So these are called, what's it again? Paraelectric crystals. Yeah. This is one mechanism that might lead to a nonlinear relationship between the P field and the E field, even if the material is isotropic and homogeneous. Yeah. So was that clear? Any questions on that? Okay. And now I'm just going to show you some definitions. So, just to make sure that you know the definitions of all the quantities, I'm going to show you the various notations used. So for linear isotropic homogeneous materials, we have that D is equal to epsilon 0 times E plus the polarization, which is proportional to E. Sorry, that's the E field, of course. Now, as you've noticed, epsilon, which is the dielectric constant of the medium, can be written as epsilon 0 1 plus chi E. And by the way, the reason to use this chi E is if chi E is much smaller than 1, let's say, for example, for a gas, chi E can be less than 10 to the minus 3. So it's quite small. So giving this number is 1 plus chi E would be 1.000 something. So it's more convenient to just give the chi directly for those materials. While if the material is has, let's say, 1.5, if the chi is 1.5, then it's more common to give the relative dielectric constant. That's this epsilon r. So then we just quote the whole thing. So you got to be careful if you're working with these materials to check which one did I get. Yeah, and if you're starting to work with the time-dependent Maxwell equations, then epsilon r is going to depend on the frequency, and then you can't be working in the time domain. So in time-dependent electrodynamics, epsilon r is some function of frequency. This means you can't work in the time domain anymore. For example, if you remember the wave equation, I think you've seen that before. We're going to find the wave equation for electromagnetics later. Then you need to be working in the frequency domain, because if you work in the time domain and you insert, let's say, if I shine light of many frequencies onto some object, well, then I don't know the dielectric constant anymore. It doesn't really exist, because it depends on the whole history of the material. So you should only work with the frequencies then in the Fourier domain. Yeah, and also this epsilon r is related to the index of refraction. In the following way, which I think we're going to look at this later in the course. I'll just quote it. In principle, it's epsilon r mu r. Mu is the magnetic equivalent, which we'll be discussing next chapter. But usually, for a lot of materials, the mu is equal to 1 more or less. There's not much magnetic glass or plastic around, so which means that the mu is approximately equal to 1. This is equal to the index of refraction. So if you're interested in the index of refraction of a material, you could just go to someone who did electrostatic measurements on an object, in principle at least. Yeah. And in this linear case, I can just write down the following equation. Of course, I can just rewrite this in terms of the E field now because the D and the E is proportional. This is now the epsilon for the material. If I write it in the following fashion, you'll see that this epsilon here is a damping factor. So it effectively dampens the electrical field inside a material. So you could just call it a damping factor or a reduction factor. Yep. And you could physically look at this in the following way. If I have some, let's say, a small sphere with some charge larger than 0, Q, then the dielectric outside is going to be polarized, of course. So if this is positive, you will see that locally the negative charges in the, well, as the dipoles align, the negative charges turn to the inside, and the positive ones to the outside, like this. So epsilon r is just some screening factor in this case. So for linear dielectrics, we could just might as well work with D or E equivalently. It's easier to work with the D field directly, usually. So that concludes the linear materials. Now what if the materials are still linear, but they're not isotropic anymore? Okay, so in general, the dielectric constant is not a simple constant, it's not a scalar. It's a tensor. This could happen, for example, in some solid, because then the atoms or molecules are arranged on a grid, a lattice. Then along some directions in the lattice, it's easier to polarize than in others. This has important technological applications as well. So for a scalar, the constitutive relation was very easy. But if you look at different directions in an anisotropic, let's see. This was the isotropic case. In the anisotropic case, di is equal to epsilon ij ej. I'm of course applying the summation convention here now. This is then just a sum. I can write it out if you want. So each component of the D field depends on all the components of the E field, then it's not quite as easy. You can't construct the Coulomb's law and all these other problems that crop up. So, yeah. Still, this only holds in the frequency domain. If we're going to be even more general, the displacement field can depend on higher order terms of the E field. And I can write this in the following way. So first, it's e to power 1, essentially. This is not the Levi-Civita symbol today. Ej, Ek. So now, if I have a field in the y direction and the x direction, it could change the field in the z direction as a product. And this is, of course, essentially E squared. This is what we mean by nonlinear, right? That it's not to power 1 anymore, it's to power 2 or 3 or even higher. Any questions on that? These nonlinear effects are typically used to, well, you could, for example, change frequencies of laser light, which is fascinating stuff. So let's leave linear dielectrics and move on to boundary conditions again to repeat those. I have an interface between material 1 and material 2. I define a normal vector, which is of length 1. You see this hat. And the boundary conditions are familiar to you now. So the difference in the parallel, let's see, in the orthogonal components of the D field is equal to the sigma f, which is the free charge. Well, free charge density. And the other one? Like this. Of course, now, if we work in linear materials, the D will be proportional to the E. And if, let's say, there's no charge density for now, then this is E2 minus E1 with an epsilon in front. Epsilon 1 and epsilon 2. So this means that for if you have two different dielectric media, the E field is not continuous even if the charge distribution, the charge density is 0. So that's actually the cause for Snell's law, that the dielectric constant changes as you cross from one material to the other. Now in terms of the potential, these boundary conditions translate in the following way. And now you see the epsilons come out. So also for the potential, the normal derivative changes as you cross the interface, even if sigma is equal to 0. So these are the two boundary conditions we would be working with if we we're interested in solving the Poisson or Laplace equations. So now, finally, we're just going to have a brief look at energy density. So if I'm inside this dielectric, how does the energy density change? I guess you've seen this in the previous course, and also it's stated in the book, in chapter 2, that if you're in a vacuum, the energy density is essentially the square of the electrical field. I write it in this way because now this was the vacuum case for the displacement field, right? So I could just think, okay, if I'm inside a material, this should be the other epsilon. And I can write it in the following way. Using the displacement field. There's one warning here though, because now we assume that the E and the D are proportional. So we're only considering the linear case. So you got to remember that this is only the linear case. It's very important. Because to do this jump is essentially to assume the following. That the D field is linear in the E field. This is explained very well in Griffiths, and the classical example for this is, of course, if you have a parallel plate capacitor. I'm pretty sure you did this in the previous course. I'm not going to go into detail. But just to remind you, if you have a capacitor, you have two wires going out, you have two parallel plates. Essentially, even if the geometry might be different, this is essentially the idea. And now if I take a slab of dielectric medium, and I put it into the capacitor, with an epsilon r bigger than 1, I increase the capacitance, or the ability of the material to store energy, which of course increases when you induce these dipoles. You need to do work to do that, because the natural state of affairs is of course to have no induced dipoles in the material. So you have to add energy to induce these dipoles. So that gives you a larger capacitance, a larger capacity to store energy. And in case you haven't found out yet, I'm going to quote the units of all the quantities we've been looking at. Just as a brief summary. So typically we give the electric field as potential per length. That's volts per meter. but in base SI units is the following. Kilogram meter, second minus cube, ampere to minus 1. Epsilon 0 is coulomb per voltmeter, which you can figure out by, let's see, yeah. It's a good idea maybe to figure out some equations to use to figure out the different units if you're ever wondering what they are. It's easy to remember the E field, for example, and this is of course joule per cubic meter or some such. So you can easily calculate the epsilon here. So it could be a good idea to work out some tricks to remember. If you only remember one of the units, then it's easy to find the others. This F here is farad, or units of capacitance. This makes sense, right? Because if I put a dielectric inside a capacitor, well, then the capacitance goes up. So they should be proportional. The D field is just the product of these two, in terms of units at least. And the polarization has the same units. Any questions on that? It's boring stuff, but I wanted to include it for completeness. Okay, so if there are no questions, I'd like to finish off with just a brief summary of what we've gone through today. Are there any questions? Yeah, by the way, before any of you leave, I would like a meeting with the reference group after, well, next week I'm gone. So after that week, I would like a meeting with the reference group. Could be any comments to if you have any comments to the exercises, lectures, midterm project, could you please contact those guys? The emails are on the webpage, and let them know if you have any ideas, and I'll set up a meeting with those guys in, well, approximately 2 weeks. I think this is week 36, so it should be 38, right? So please come with any comments so we can make the course even better. Okay, so, and also I wanted, I think we're ahead of schedule on the lectures. So are anyone interested in a crash course in Python? Let's say 1 lecture hour, a few tricks to get you started on Python? I see a lot of nodding. I mean, you don't have to use Python. It's just my favorite. So if you want to use something else, you just leave that lecture. But as I say, a lot of nods. I think we spend 1 hour on Wednesday to give a brief introduction so you don't have to figure out everything for yourself. Is that okay? Great. Okay. So let's see. Summary. If we're inside a dielectric medium, E causes P. The electric field causes polarization. This is because we have induced dipoles or oriented dipoles. So either we orient some polar molecule, a molecule that is already polar in nature, like hydrogen chloride, alcohol, water, or we just induce something. Let's say we have a neutral atom, but the nucleus and the electron clouds is pulled in different directions by the E field, and this is the induced effect. Okay? Well, as we said now, if I have a material, then E causes a polarization P, but if you don't know, you can't really tell how much beforehand, because the P field sets up a new electrical field, and then this will change the P, so you have to sort of solve this self-consistently. This is very complicated, but we found the equations for a new field, which is the electric displacement field. Plus the polarization. Electric field plus polarization, that's the displacement field. And this equation is always true, of course, even if the P is caused by E in some nonlinear, non-isotropic, funky way. And this fulfills the Gauss law. So, and to solve any electrostatic problem, we need some sort of connection between E and D, the electric field and the electric displacement field. And this is called a constitutive relation. These are important, and they're in general very hard to figure out. So you can't really tell beforehand what this looks like. But if the E field is not too strong, and if you have some sort of standard simple material like glass, then you can assume linearity. And for a linear isotropic homogeneous medium, it's just that the D field is proportional to the E field, with epsilon being the proportionality constant. If, however, it's not an isotropic medium, let's say you have a crystal, then there's then epsilon is a rank 2 tensor. It's still linear. It's still homogeneous. But it is anisotropic. Yeah, let's see. Yes, and at the end here we saw that the energy stored in the electric field was changed somewhat by the introduction of a dielectric medium. And this had essentially the effect of increasing the capacitance in, let's say, a capacitor, or the inadvertent capacitance in, well, if you have some sort of transmission wire, for example, it will have some capacitance which you might not even want, but it will still be there. Yeah, and we saw how the boundary conditions was affected by the dielectrics as well. And this actually means that even if there's no charge density anywhere, no free charge density at least, we still get boundary conditions that introduce jumps in the potential, or the normal derivative of the potential, and the orthogonal component of the electric field. So anyway, if you're in doubt about what is safe to assume and so on, you should start out by this equation, because that's the definition, and the Maxwell equation, and work your way from there. And if you make sure you don't assume anything that's dangerous, or let's just say wrong, then you should always be fine. Okay, any final questions or comments? Okay, Wednesday then.